All right, welcome back to Physics 425. Today we have two main goals. The first one will be to postulate and then come up with a bit of an interpretation of a quantum mechanical wave function for a Bose-Einstein condensate. So for the particles that are collectively in the ground state of some boson system. And the second goal will be to try to determine a critical velocity that we're going to associate with superfluidity. In particular, what we'll find is that when the particles in the condensate move at a velocity that's greater than the critical velocity, then superfluidity, or fluid flow without any dissipation, is destroyed. And in fact, that's going to have some interesting consequences that we'll point out closer to the end. Okay, so to start, what we just do is we make a note of the fact that we have seen some experimental evidence that we can interpret some of the phenomenon that we associate with superfluidity in terms of a two-fluid model. Okay, so we have seen experimentally that below the superfluid transition temperature, which is about 2.17 Kelvin, liquid helium behaves as if it's composed of two interpenetrating fluids. So the two fluids, one of them is known as a normal fluid component, and this normal fluid has entropy and it has a viscosity. So the normal fluid fraction is viscous and has a non-zero entropy. So we know that dq is TdS, and so if there's some non-zero entropy, then this normal fluid can transport heat. Then the other part is the superfluid, and so the superfluid fraction flows without dissipation. So it has no viscosity, and it also has zero entropy. Remember, the zero entropy was deduced because the superfluid fraction tends to flow from a cold region to a hot region, and so it can't carry heat without violating one of the laws of thermodynamics. Okay, so what we do is we identify the superfluid fraction with the condensate, so that is the particles in the ground state, so in the lowest energy ground state, and the normal fluid is composed of particles in excited states. So these are thermal excitations into higher energy states. And so in the last couple of videos, we've written down what that excitation spectrum looks like. There is first a linear part. If you plot E versus momentum, or versus K, And so that linear part was called the phonon states. And then it went through a maximum and then into a minimum, and around that minimum we called those the roton states. And so all of those particles in those states are part of the normal fluid fraction. Okay, and so what we could do is we could make a plot as a function of temperature of what this two fluid model looks like. And so we'll say here's the superfluid fraction, and then the normal fluid fraction looks something like this. And so this is the rho n. And so right around here where the superfluid fraction goes to 0, this is the superfluid transition temperature. So as you go lower and lower beneath this T lambda, you get more and more particles entering the superfluid or the condensate, the ground state energy level. And so we have all these particles in the lowest energy level, and this corresponds to the condensate. And then you have your higher energy levels where you have some particles occupying these kinds of states. And so these are the thermal excitations, and they make up the normal fluid. Okay, sorry, it's thermal excitations. Maybe I can draw that a bit nicer. Thermal excitations. Okay, so today we introduce a wave function that describes the entire condensate. And we'll write the supercurrent. And so what I mean by supercurrent is not the flow of charge, but mass flow, a flow of mass without any dissipation. And we're going to find that that's going to be written in terms of the phase of this wave function. Okay, and so we start with a bit of an analogy. So apart from superfluid flow in, say, liquid helium, and charge flow without dissipation in superconductors, there's actually one other type of current that flows without dissipation, and that's electrons in atomic orbits. So atomic electron orbits are the only other known currents that flow without dissipation. So if you imagine electrons orbiting some kind of nucleus, that's a flow of charge, and there's no dissipation associated with that flow. So each electron in an atom occupies a quantum state, which is an eigenfunction of an Hamiltonian. So what we're going to do is, by analogy, we're going to say if we have in our liquid helium a mass flow without any dissipation, by analogy, we're going to write down a wave function for that entire system, that entire condensate, and we'll try to make that an eigenfunction of some kind of Hamiltonian. So in 1954, by analogy, it was London who argued that superfluid currents in liquid helium are also quantum in nature, and that a wave function extends throughout the superfluid volume. So that was a postulate, which is now supported by experimental evidence. You could also think back to when we were talking about Bose-Einstein condensation for the first time. One of the criteria that we found was that when the wave function of a single particle occupies a volume that is approaching or greater than the space available per particle, wave functions of adjacent particles overlap, and that kind of corresponded to when Bose-Einstein condensation occurs. And so you have these overlaps of the wave functions of neighboring particles, and then after that, what we can do is write down a single wave function describing all of the particles in the Bose-Einstein condensate. Okay, so the condensate wave function that we'll write down is phi, which is going to be a function of position. It'll have an amplitude and a phase. So phi 0 is the amplitude. What we're going to do for now is assume that this amplitude is independent of position, but in general, it could be position dependent. Can depend on position. But to start, or for now, we assume that phi 0 is constant. Okay, and then the other thing we have is a phase factor in this exponential, and we've labeled that S, and it is position dependent. So if we wanted to calculate a momentum, we would operate on this wave function with the momentum operator. So the momentum operator is minus I h bar times the spatial derivative, or the gradient. And so if we operate on our condensate wave function, what we get is minus I h bar times the gradient of our amplitude and our phase factor. Because we've assumed this amplitude is a constant independent of position, what this would come out to be is I h bar phi 0. And then we have to we'll get the exponential back, and then by chain rule, we have to multiply by I times the gradient of S. Okay, so we have an I times I, which cancels, and so we could write this as h bar times the gradient of S times, well, phi 0 times e to the is is just the original wave function back. And so we get our original wave function back. And so this is our eigenvalue, which corresponds to the momentum we're calculating. And so we get that the momentum is equal to h bar times the gradient of the phase. And so, at least for this postulated wave function, the momentum of the condensate is determined by the phase factor. So we interpret this momentum as the momentum of one particle in the superfluid. Right, and so that particle is at position R, and so if we had some other particles in the superfluid with different positions, then we would just have to take the position derivative of the phase factor to find their individual momentum. So if we divide by the mass of one of the helium atoms, we could find the superfluid velocity, Vs, and that would be what? P is the mass of a helium atom times its velocity, or Vs is h bar over m4. The velocity was h bar times the gradient of the phase. Okay, so when the superfluid is at rest, so let's suppose you had a dewar of helium and you've pumped on the vapor pressure and you've cooled it below T lambda, and so now you just have a superfluid at rest in your dewar. Well, if Vs is equal to 0, that's going to imply that the gradient of the phase is equal to 0, or that this phase is constant. So the entire condensate has the same phase. Okay, so what you could do next is you could try to get your superfluid in motion. Maybe you have some capillaries or something like that, and you start your superfluid flowing through these capillaries. So when the superfluid velocity is uniform and constant, then S varies smoothly in the direction of Vs. So the gradient of S has to be a constant, and so that means S is a linear smooth function of position. Okay, what that means is if you have this uniformly moving superfluid, there can be no abrupt changes in S throughout the entire superfluid volume. What that allows us to do is to make a bit of a qualitative, or to develop some kind of qualitative understanding of how constant superfluid velocity can be maintained for long times. So think of the following scenario. You have liquid helium above the superfluid transition temperature, so it's all normal fluid, and you somehow devise a device where you can rotate the dewar. So while it's all normal fluid, you start rotating the dewar and the fluid will rotate with the dewar. Then you cool down the superfluid, so below T lambda, and after that you stop the dewar rotating. What you'll find is that the superfluid will keep flowing around in a circle indefinitely, as long as you keep it below the superfluid transition temperature. So if you were to imagine a sudden change in Vs, so if you're going to have a sudden change in Vs, you're going to have a change in the gradient of the phase of the wave function. So since this phase is smooth for, say, initially we have a uniformly moving superfluid, we have that this gradient is about constant. And so all particles in the condensate have the same momentum. So if you suddenly try to change Vs, and therefore, so if you change Vs of a particular particle, then you have to change the phase factor, so S of R of one particle. Well, the superfluid velocity of all of the other particles also depend on that phase. And so if you change it for one particle, you change it for all of the particles, and they all have to have kind of an abrupt sudden change to their velocities. So it must also change this phase factor of all particles in the condensate and V of the entire condensate also. So what does that say? Must also change the phase of all particles in the condensate and the velocity of all particles of all condensate particles. And so that's very unlikely. It's not easy to change the velocity of a single particle in the superfluid, because that would simultaneously affect the velocity of all the other particles. Okay, and so that's kind of a collective behavior of the superfluid. It's no longer a set of kind of independent individual particles. It's a collection of all particles doing the same kind of motion, and changing one of them would affect the motions of all of the others. Okay, so that's a bit of a qualitative understanding and an introduction to this condensate wave function. The other thing that I wanted to do was to talk about the so-called Landau criterion for superfluidity. It's going to turn out that it's not just sufficient that we have a Bose-Einstein condensate for superfluidity to exist. And so we're going to come up with another criteria. And so we'll start in the following way. We're going to consider some superfluid, which we called helium-2, and we'll set this to be at t equals 0. So, as close to t equals 0 as we can get. And we'll have this moving in a narrow tube. So here's our tube. It's filled with superfluid, and it's moving with some velocity. The claim is the following. So above a critical velocity, which we'll call V critical, superfluidity is destroyed. Because when condensate atoms collide with irregularities in, say, the pipe wall, they are removed from the condensate and promoted to excited states. And so in the case of liquid helium, those excited states would either be phonon states or roton states. And so this is a bit of a contrast of what we just talked about. We talked about there being this phenomenon where it's hard to change the velocity of a single particle in the superfluid, but it's going to turn out that once you get above a certain critical velocity, then you can excite some of these particles out of the condensate and into excited states, and associated with that is going to be some change in kinetic energy of the condensate and therefore dissipation. Okay, and so these excitations are created with or associated with an equivalent loss of kinetic energy in the superfluid, right? So if we raise one helium atom into a higher energy level, that energy comes out of the superfluid. And so that means when this critical velocity is reached, the flow in our helium-2 ceases to be frictionless. Okay, and so what we want to do is we want to see if we can estimate this critical velocity. So estimate of V critical. It'll be based on conservation of energy and conservation of momentum principles. So to start, we imagine a large mass M moving at a constant velocity v through a superfluid at rest. Okay, and so the picture is maybe we have some tube of superfluid, and this will be the rest frame of that superfluid, and then we have some mass m, capital M, and it's moving with some velocity v through that superfluid. We've chosen this geometry, but equivalently it could be this mass m inside this tube at rest and then the superfluid rushing by at velocity v. So that's an equivalent picture. So what we're interested in finding is the minimum value of V, which creates an excitation. So an excitation of a helium atom initially in the condensate to either a phonon state or a roton state. And if we can find that minimum velocity, that is going to be this critical velocity that we're trying to find. Okay, so what we do is we suppose that the excitation in the superfluid is of energy epsilon p. So p is momentum, could be epsilon k if you like. And so that excitation also has a momentum p is equal to h bar k. So we've taken a particle that was initially part of the condensate, had zero energy, and then promoted it to an excited state with energy epsilon p. Okay, so let's write down the conservation of energy. So initially we have this large mass moving with speed v, and so there's kinetic energy 1/2 mv squared. And then after that, what we have is our large mass has some new velocity v1, and so it has kinetic energy 1/2 mv1 squared. But we've taken one of the superfluid particles, which was initially in the condensate with energy 0, and promoted it to an excited state. And we can write down conservation of momentum as well. In the rest frame of the superfluid has no momentum, and so initially the only momentum is that of the large mass. But afterwards, the large mass has its velocity changed, and the excited particle has the excited helium atom has momentum p. Okay, so from this momentum conservation, we can say that v1 is going to be equal to v minus p over m. What we want to do is we want to calculate v1 squared so that we could substitute that into the conservation of energy expression. So v1 squared is v1 dot v1, and so that's going to be v squared minus 2 p dot v over m, and then plus p squared over m squared. Okay, and so this expression for v1 squared goes into our conservation of energy, and so what we get in that case, 1/2 mv squared, so this is a capital M, equals 1/2 m v1 squared, but now that's going to be v squared minus, let's see, it's just going to be p dot v for the next term, and then it's going to be plus p squared over 2m, and then we still have the energy of the excited particle, excited helium atom. Okay, well, we get a cancellation here, and we have epsilon minus p dot v plus p squared over 2m is equal to 0. Okay, so that's something that we've extracted from our conservation of energy and momentum. What we're going to do is we're going to assume that our mass m, the mass of this particle moving through the superfluid, is very large. It's large enough that the first two terms in this expression dominate the third term on the left-hand side. So it's very large, such that this p squared over 2m is negligible. Okay, so if that's the case, then what we're left with is epsilon p is equal to p dot v. P dot v is pv cos theta. Okay. Now, cos theta, the biggest cos theta could possibly be is 1. Okay? And remember, what we're looking for is a minimum in this velocity. And so if we were to solve for the velocity, we would get epsilon divided by p cos theta, and we want the smallest possible velocity, so we would take cos theta is equal to 1. That's the biggest it could be. So we must have the following, that epsilon p must be less than or equal to p times v. Okay? Because if we set cos equals to 1, that's the biggest value of epsilon we could have. Or alternatively, v must be greater than or equal to epsilon p over p. So this is the condition for conditions for excitations out of the condensate. So that is, or in other words, any v greater than epsilon p divided by p causes excitations, and therefore the flow is not frictionless or not without dissipation. There's energy loss. Okay, so to achieve frictionless flow, we require then speeds v that is less than a critical velocity, which is defined by the value of epsilon divided by p that is a minimum. So we want to find the minimum of epsilon divided by p. That's going to define our critical velocity, and to have flow without dissipation, our superfluid has to move with a velocity less than this v critical. So values of p that minimize epsilon p over p are determined from the condition that if we take the derivative of epsilon divided by p with respect to b and set that equal to 0. So we want to find p that minimizes this ratio, substitute that into epsilon over p, and that will tell us the critical velocity. So we could do some manipulations here for a general epsilon of p. So if we take this derivative, we would get 1 over p d epsilon dp minus, let's see, epsilon divided by p squared. And that would have to be equal to 0. And so we could cancel one factor of inverse p, And our condition is, therefore, that d epsilon dp must be equal to epsilon divided by p. So let's do some examples, and let's calculate some actual critical velocities. So example 1. This is going to be the critical velocity of a system of non-interacting bosons. Right? That's maybe the simplest case we could think of. In that case, the energy is h bar squared k squared over 2m, or equivalently p squared over 2m. And so we could evaluate then d epsilon dp is just p over m, and epsilon over p is p over 2m. So what we need to do is to find p that minimizes epsilon p over p. We require d epsilon dp equal to epsilon over p. So d epsilon dp is p over m, and epsilon over p is p over 2m. And so that's the condition we have to solve for p. But of course, there is no solution for that. We have the condition that p is equal to p over 2, and so the only solution in this case is p equals 0. And so that means the critical velocity, which was the minimum value of epsilon p over p, is, well, epsilon p over p was p over 2m, and that was minimized when p equals 0, and so it's 0. And so that's kind of an interesting result, because that tells us that the critical velocity for a system of non-interacting bosons is 0. So as soon as you have your condensate flowing, you immediately get excitations out of the condensate into excited states and associated energy losses. And so you never have superfluid flow or friction-free flow for a system of non-interacting bosons. So the critical velocity of a system of free bosons is 0. So in these systems, flow of any velocity is sufficient to create excitations out of the condensate. There's no frictionless flow, and there's no superfluidity. That's a surprising and non-intuitive result. It tells us that if you want to have superfluid flow, you're going to require some kind of interactions. Okay, so let's check Landau's spectrum for epsilon versus p. So we've written this down a bunch of times. So there's a linear part, then there's a maximum, and then a minimum. And so these were the phonon states. And in the phonon states, we had a linear dependence of epsilon on momentum, and so the slope of this line is just going to be u1. And in the Roton states, which were here, epsilon p was equal to a delta plus. We had a k minus k0, but if we just multiply those k's by h bar, we get p minus p0 over 2m. Okay, so let's do the phonon critical velocity. What we'd like to have is a critical velocity that is above 0 so that we could have some superfluid flow. Okay, so what we need to do is we need to test this condition epsilon over p is equal to d epsilon dp, and solve for p, which minimizes the ratio that we want. So epsilon p over p is just u1 in this case, and d epsilon dp is also u1, right? It's just a linear function, so the ratio is equal to the derivative. And so therefore, epsilon p is always equal to d epsilon dp. So this is satisfied. For any value of p along the linear phonon curve. Okay, so V critical, we said, was going to be equal to this ratio when it was a minimum. That ratio is epsilon is u1 times p, and then we divide by p. We could pick any value of p, it doesn't matter because it's going to cancel anyways, and we just get u1. And so for excitations into phonon states, so excitations out of the condensate into a phonon state, the critical velocity is V critical for the phonon states is U1. And in the last video, we looked at some measurement of Landau's excitation spectrum. And from that experimental data, U1 was around 239 meters per second. I mean, that's a pretty big velocity, right? 240 meters in a second. So as long as you stay below that critical velocity, you won't have excitations out of the condensate into phonon states. One more thing for us to do is to check the critical velocity for the Roton states. Okay, so epsilon of p is delta plus p minus p0 squared over 2m. All right, so d epsilon dp is going to be what? P minus p0 over m. and this ratio epsilon p over p is going to be delta over p plus, well, there's not much we can do, p minus p naught squared 2m divided by, with a factor of p in the denominator. Okay, so therefore p that minimizes our ratio epsilon divided by p is determined by equating these two expressions. And so it's p minus p0 over m is equal to delta divided by p plus p minus p0 squared over 2mp. So the first thing we'll do maybe is multiply by 2mp so that we can get rid of the denominator. So when we do that, we would get 2p squared minus 2p0p is equal to 2m delta plus p minus p0 squared, which we can expand to p squared minus 2p0p plus p0 squared. Okay, and so we do have one cancellation here. And so we could solve for p squared. So we have 2p squared minus p squared. We would have p squared is equal to p0 squared plus 2m delta, or the p that's going to minimize epsilon divided by p and determine the critical velocity is p0 squared plus 2m delta. Okay, so before we actually calculate this critical velocity, we can again think of those neutron scattering results that experimentally determined Landau's curve, or confirmed it. From that data, p0 squared is something like 4 times 10 to the minus 48. And so that would be in kilograms meters per second squared. And 2m delta is like 2 times 10 to the minus 49 in the same units. These numbers are determined using p0 over h bar is 19.2 nanometers inverse, and delta over kb is like 8.65 Kelvin, and this big M was 0.16 times M4. So this first term is more than 10 times bigger than the 2m delta, and so what we can say is that p0 squared plus 2m delta, to a reasonable approximation, or say is just p0 squared within, is fairly close, or p is approximately p0. All right, and so that means that the minimum value of epsilon divided by p is equal to delta divided by p0 plus, then what we had is a p minus p0, but now remember we're setting our minimum value is determined by when p is equal to p0, and so we get p0 minus p0 squared over 2m p0, and so this all just vanishes, and therefore V critical for our Roton states is about delta over p0, and if you put in numerical values, that comes out to be about 59 meters per second. And so this is critical velocity to excite let's say atoms from the condensate into roton states. And so it's a bit of a surprise that the critical velocity to get into roton states, which are higher energy states, turn out to be lower than the critical velocity required to excite particles into the phonon states. But nevertheless, that's what it is. And so we have our two critical velocities, and as long as our condensate is flowing at a velocity less than, it turns out, the critical velocity for the roton states, we should maintain frictionless superfluid flow. All right, thanks very much. That's where I'll stop for today, and I will talk to you next time.